This will be an N-part series where we'll be exploring what Terraform is, what we can do with it. We'll be building a lot of infrastructure as well. We'll try to understand how we can work with it, what are the concepts around it, what are the terminologies around Terraform, and basically get our hands dirty with it. This is part zero. Being in the IT industry, being in the programming world, we understand that zero is generally where the indexing starts from. So this is very basics, fundamentals. We'll be targeting just the terminologies here, and I'll show you a slight hint of some Terraform code. It'll lay the foundation of all our future sessions. Welcome to the series. Let's start with what Terraform exactly is, right? We all know that it's an infrastructure as a code tool. It allows us to define infrastructure, whatever we have in our cloud, as code. That gives us the power to essentially version control it, find out exactly what our infrastructure looks like, change it as we see fit, detect drifts if at all, revert back infrastructure, and all these really powerful capabilities, right? And the best part about Terraform is that we are not limited to just one specific cloud. It's not that with Terraform you're limited to AWS or Google Cloud or Azure or something like that. As long as there is a provider that exists, we'll come to what providers are in just probably one or two next slides. As long as there is a provider for that cloud provider, we can create and modify and manipulate infrastructure on that cloud provider. We'll primarily be using examples around AWS, but that is just so that we get a hang of what Terraform is. Our objective is not to understand what AWS is, what cloud is, what IAC is. Our objective is to understand what Terraform is. There are some keywords that whenever we want to start with Terraform, we need to understand, we need to be aware of them. Like I mentioned, the first thing is providers. Providers are essentially the plugins which enable Terraform to communicate with the cloud provider. We'll be going into depth into all of these. For the scope of this session, we'll just be touching upon what they are. The more we progress with the sessions, the more deeper we'll go with these keywords, with what they do and how they work. For the timing, let's start with providers, right? As you can see in the code snippet, we specify that we want an AWS provider. We give it a specific region, we give it a profile, right? And the way this works is that Terraform understands this code snippet, right? And when it sees this code snippet, it understands that, okay, I need to go and fetch the AWS provider binaries. And these providers are mostly open source. They're written by the community. I'm sure a lot of AWS developers would have written the provider for the AWS provider here. And what that allows is these providers essentially then latch onto Terraform and the capabilities that Terraform provides. And they work in tandem with Terraform to build that infrastructure. Each provider comes with its own set of resources and data sources. So for example, in the code snippet that you see, we have an AWS S3 bucket. Now, obviously, this will not be present in Azure or GCP, right? S3 buckets are something very native and very limited to AWS. But since we mentioned that the provider is going to be AWS, we have the ability to use S3 bucket as one of our resources. What the resource structure, the resource concept does is that it defines an actual infrastructure bit in our cloud infrastructure. If you can notice that we at no point are describing how we want the infrastructure to be spun up. We just define what we want, right? So this is what we call a declarative approach. We define what we want, and then Terraform takes care of how it's going to build up. It'll create a proper graph of dependencies of what needs to be created before, what needs to be followed after that, so on and so forth. Our objective is just the end result. This is how we want our final infrastructure to look like. Resources can be of a million types. Each provider has hundreds and thousands of resources that they have. VPCs, RDS, S3 buckets, EC2 instances, EKS clusters, etc., so on and so forth. Do check out their documentation. They have amazing documentation of the resources that they have and the data sources that we have. Speaking about data sources, let's move on to that. So data sources are essentially similar to resources, but they differ in the bit that it's not actually creating any infrastructure. Data sources are mainly meant for computing of specific things. For example, in the code snippet that you see here, we are creating a simple IAM policy document, right? And we define that, okay, these are the actions that we want, these are the resources that we want, and this is what the effect is going to be. Once we execute this, no resource is yet created on AWS. We have just defined what it looks like, what it's going to be, and we get some more parameters. Like we can probably convert this into a JSON. We can get an AR now when we create a resource out of it. We'll come to that as we see more and more examples. What this also allows us to do is, if you have a specific resource that is probably defined outside of the scope of Terraform, you can pull that in. You can fetch data about those resources in your Terraform code. They might not still be managed by Terraform. They might still be managed in whatever way they were being managed previously. But at least you can interact with them. You can probably you can probably fetch their ARN or get some endpoint URLs. Example, we'll see what comes up. Moving on to the next one, we have variables. I think variables are central to most programming languages, if not all. So is the case with Terraform, which under the hood uses HCL. This syntax is called HCL, HashiCorp configuration language. What variable allows us to do is, instead of hard coding everything, right, we can define variables which then can be fed values at runtime, which is a very typical concept and understanding of what variables are. You have three different types of variables. You have input variables, you have output variables, and you have local variables. Input variables are essentially variables that demand input from the end user. They can either be coded up in a file, in a terraform.tf file, or they can be fed at runtime when you're applying the infrastructure or planning the infrastructure. Output variables, on the other hand, are a lot like how we have return values in methods and functions of programming languages. For a snippet of code, it will basically give an output back. A good example of output variables would be, say, the invoke URL of an API gateway. You created an API gateway using Terraform, but you need that invoke URL to actually interact with the API gateway, right? Maybe you need to send it to Amplify, or maybe you need the front-end application interacting with that API gateway, but you need that URL. Now, you can't go to AWS and then find out the URL from there. You can, but that's just counterproductive. So Terraform gives us the ability to return output variables onto the console that it is being applied from. Local variables are limited to the scope of the file in which it exists. It's a lot like how we have local variables within functions. The scope is limited to that function itself. The moment the control goes out of the function, that local variable is garbage collected. Similarly, here we can define specific things. For example, if we want to define a constant naming convention or a name that we're going to follow, and it's going to be used several times in the same file, we can define a variable for it. Because this might not be something that we want the end user to be inputting, right? But we do not want to keep on typing the name again and again. That's just bad practice. So that is where local variables come into play. If you see the example in the code snippet, you notice that we have a simple block which says locals and then name. You can refer that name anywhere in that entire file. That wraps up our variable side of things. Moving on to state file. State file is extremely important when it comes to Terraform. It is central to how Terraform works. Whenever we plan and apply any resource, Terraform will generate a state file. It will compare with you what infrastructure you have deployed against your state file. It will create a diff. It will find out the difference of what Terraform wants to do and what is actually deployed, and then generate a plan of what it needs to do. This state file is easily accessible. It's basically a huge JSON file that we can read, we can understand, we can see the details from. And this state file is what also enables us to synchronize infrastructure between two developers. For example, if there's a team of 5 infra engineers, DevOps engineers, say, working together on a same set of infrastructure, say they are all working on the same Kubernetes cluster, we are all making modifications every now and then. This state file there has to be some way to synchronize the state file, right? And once the other developers have the state file as well, they can safely apply any changes that they need. In order to enable this synchronization, we'll be creating some infrastructure today. Like I said, that infrastructure, that code will be the foundation of all our future sessions. So in this session, we'll be creating just an S3 bucket and a DynamoDB table. That S3 bucket will act as our state source. All our state files, whenever you make any modifications, will be stored and updated in that S3 bucket. And the DynamoDB table will essentially be used to create a locking mechanism so that two people cannot simultaneously make changes on the same set of resources, because that might just lead to weird configuration and just inconsistent configuration. We want to avoid that. Right, so let's jump onto the code that I feel is the most exciting bit. Generally, the convention is that we create folders and we start with three or four basic files. We start with a main.tf, a vars.tf, out.tf, and a terraform.tf vars. This is a completely logical separation. This is only for the developers and the engineers. Terraform barely sees any difference in the .tf files. In fact, if I understand correctly, Terraform basically clubs all these files into one temporary file and works along with it. So once we have 3 empty files created, we dedicate that the main.tf file will be the place where all our resources are defined. vars.tf will be where all our variables are defined, input variables are defined. Out.tf will be where all our output variables are defined, and terraform.tf vars will contain any input variables values that we have specifically set. If a default value of the input variable does not exist, and if the variable value does not exist in the terraform.tf vars, then Terraform will prompt you while you're applying or planning the infrastructure to give a specific value. Having said that, let's get started. Let's first start with a very basic provider block, right? As you saw in the code snippet during the presentation, it's a very simple provider block. We specify that, okay, we want an AWS provider with a default region, and I want the personal CLI profile to use. Right? This personal profile that I have, this is basically the same profile that I have in my home.aws folder. This profile needs to have permission to modify resources. If this profile does not have, say, the ability to create an EC2 instance, Terraform will not be able to create that EC2 instance. It essentially uses the AWS CLI and the AWS APIs to create the infrastructure. As mentioned just a few minutes back, we'll be creating an S3 bucket and a DynamoDB table. But in order to do that, since S3 buckets need to be globally unique, right? We'll create a random string, and we'll append it to our S3 bucket's name, just so that we do not have any clashes when we are creating that infrastructure. So if you can see, this is another example of a resource block. This is something I believe all providers have. This allows us to create a random 16-letter long string. We can have special attributes that we specify, which describe the characteristic of this random string. As you can see that we have asked that no special characters be included in it and no uppercase characters be included in it. But it'll essentially be a lot of lowercase characters of 16 letters long. Let's jump into meat of it, right? The S3 bucket. As you can see, I just mentioned that we'll be appending the the random string here to the bucket name. The way that we define resources are generally you start with a keyword resource. You specify what type of resource you want, whether it's an S3 bucket or an EC2 instance or an EKS cluster, whatever you want to spin up. You give it a name. Now, this name is something that you will be referring to in wherever you want this S3 bucket to be used, right? But that is just within Terraform. So for example, the name that I've given here is state bucket, and the bucket name is something else. So when we go to AWS CLI, we will see that the actual bucket name is something else. It's obviously not state bucket. But whenever we want to refer this bucket in Terraform, we'll be using state bucket, right? On to the next one. Let's give it some more parameters. We'll tweak how our bucket looks as well. We'll maybe enable encryption. We'll give some more control over how this bucket behaves. Since this bucket is extremely sensitive to us, this bucket is going to be our state source. We do not want this to be destroyed, right? Because that basically means all our infrastructure state files are suddenly lost. We want to prevent any destruction of it, any accidental destruction of it. If it is absolutely required, if it's a hard requirement that you have to destroy, then we'll probably get rid of this bit and work with something else. But at least for the scope of this, we'll add it. Let's move on to the next. Let's enable versioning, right? We want to track how our state files are changing. Now, this is essentially we are adding two ways of tracking our infrastructure change. One on the S3 end, where it shows how our state file is changing, and one on the Git side of things. The Git side of things will only show how our Terraform code is changing and not how the state file is changing. On to the next, let's enable encryption, right? I can't stress this enough that these state files are really important to us, and we want to be as secure and keep them as safe as possible. So having some server-side encryption is obviously a good practice, even in general. Let's move on to the DynamoDB table, right? This DynamoDB table will essentially be used by Terraform to lock our resources. It will prevent any simultaneous changes. If you're familiar with the concept of semaphores and mutexes on the programming side of things, this is very similar to that. Whenever we make any change to a set of infrastructure with a specific lock ID, Terraform will ensure that no other person can lock that file, right? So it tries to get a lock. If it can't, it means it's already locked by someone else, and you cannot make any changes to that. Let's tweak this a bit. We want our DynamoDB table to have a billing mode of pay per request. For more details on what are the possible values that we can have here, I urge you to check out the documentation. We have amazing documentation and have detailed properly what all is allowed and how we're going to go about it. Our objective is not to go into the nuances of AWS, but to understand what Terraform is and how it works. So this is why I'm sort of skipping over the details of all these. Right. So with that, we have essentially completed whatever we had to create, at least for the basic bit. Let's actually try to apply all this and see what it does. Just to show you that I don't have anything already deployed, I'll run an AWS S3 LS. As you can see, the output is empty. I don't have anything set up in my personal AWS account. Let's change that. As I mentioned, we'll have 4 files: main.tf, out.tf, terraform.tfs, and mass.tf. At the moment, every file but main.tf is empty. Eventually, when we progress with the upcoming sessions, we will be populating those and we'll be utilizing those as well. To work with Terraform, the first objective is to initialize it, right? Any Terraform application process goes about in 3 steps: init, plan, and apply. Init is a one-time thing. So for a set of resources, we need to initialize it just once. Once we initialize it, it'll create a local folder called .terraform where it'll store all your providers, all binaries, all plugins, whatever it requires. Just to show you what I mean, I printed out all the hidden folders here as well, which at the moment does not exist. Right. Let us initialize Terraform. As you can see, it'll fetch the latest provider, latest version of the HashiCorp AWS provider and the random provider. And once it has done that, it will create the local .terraform folder and it will store everything there. As you can see, it created a folder called .terraform, which has a bunch of files. It also created a file called terraform.lock.html. This is something new that Terraform has recently introduced, I believe, with version 0.14. What this allows is that it allows us to pin the exact version of the providers. This is very similar to how we have log files in other programming languages. For example, I believe JavaScript has that. Node.js has a package lock concept. Some package managers in Python have that as well. Similarly, we have it here as well. We'll check out the content of terraform.log file, and you'll see that it has it has hashes of the providers that we have. Once we have initialized Terraform, we will run a plan. This plan will compare what we have in Terraform code and what is actually deployed, create a diff, and give me an output of what all it's about to do. And it's very intuitive when it prints out this plan output. It'll very clearly tell us what all it's going to add, what all it's going to change, and what all it's going to destroy. Since, as I just mentioned, that my account is a completely fresh account, there's nothing deployed there, there's no infrastructure there, so we will not have any modifications or destructions. Any plus sign here, any green plus sign is an indication that it will be added. It's an addition and not a change. So here we notice that it's saying that it will create 3 resources, right? Which, if you relate back to our Terraform code, is true as well. We have a DynamoDB table as a resource, we have an S3 bucket as a resource, and we have a random string as a resource. We can find that here as well, the same random string, the state bucket, and finally the DynamoDB table. It is generally advised that you go through what this plan output prints out so that you can understand exactly what is happening, find out if it's doing something that probably is not intended. Ideally, any application should be driven by a proper peer review process. Maybe use some form of automating your infrastructure, get a CI/CD using Atlantis or any tool of your choice set up, review it, and then apply infrastructure. Once we've gone through the output of the plan, we can run a Terraform apply. This will internally it will perform a plan again and just ask for a prompt whether we are confident that we want to apply this. Terraform is very strict about this. It will only accept yes as an answer. If I even type Y or YE or just yeah, it will not. Anything but yes is considered as a no. Since I'm fine with that, I will write down yes. It will gradually give me output of what all it is doing, and it will give me a constant log of what all has been done, how long it took. For example, the random string creation took just about less than 1 second. That's why it's given 0 seconds. And we have an ID. As you can see, it's a 16 letter long random string. It has numbers as well, but it does not have any special characters, neither does it have any uppercase, which is what we specified in our resource as well. Once all this is done, Terraform informs that, hey, you're done. You're good to go. Now, if I run AWS S3 LS, I should be able to see at least one bucket with state bucket dash this ID here, which is exactly what we see. So there it is. That is an example of how we can create Terraform, how we can create infrastructure on a cloud provider using Terraform. Now, if you want to wrap this up, if we say, for example, I do not want any extra charges associated with my account, since this is only for demo purposes, right? What I can do is I can run a Terraform destroy as well. This will go through my current file, my current folder, see what all resources are being created, and destroy them all. This obviously might not be the best thing to do in all the cases, but again, if you're confident that this is what you need, feel free to go ahead. Here, it gave me a warning that instance cannot be destroyed. Now, if you recall, we had specified in our code that that state bucket is very sensitive, and we do not want accidental deletion of any of those buckets, right? This is where that plays in. Since we have specified lifecycle.prevent destroy is set to true, Terraform is not going to let us destroy that. In order to force the destruction, since that is our purpose, we can just comment this out. Once that is done, we can run a Terraform destroy again. This time it won't be giving us any uh, complaints, any warnings whatsoever. It'll give us an output that, okay, we have 0 to add, 0 to change, and 3 to destroy. As expected, we had created 3 resources, and we want to destroy 3 resources now. So again, it's very stringent about what it accepts as a valid input. Anything but yes is basically rejected. Once that is done, again, it'll print out a set of logs of how long it took to create to destroy each of the specific resources. Once it is done, it'll just tell me, yeah, destruction is complete. So with that, we wrap up our part 0. There will be future such sessions. We'll be gradually progressing on not just on the complexity of infrastructure, but also complexity of Terraform code. I'll try to keep it as simple as possible so that it is not just intuitive to understand, but also acts as an incremental step over the previous session. And it goes without saying that every session will depend on the previous sessions, and they will basically build on it. Thank you, and have a nice day.